A comet 5 kilometers wide and traveling over 100,000 kilometers an hour has just been discovered. Scientists have calculated that it's on a collision course with the Earth and will impact within the next 24 hours. Humanity can only cry and head for shelters with the realization that civilization is at an end. The comet hits the Earth with the impact of a 100 million megaton explosion. The entire planet is engulfed in flames as 5 billion people are immediately vaporized or poisoned by toxic fumes. Those who do survive suffer through a decade-long nuclear winter and ultimately starve or freeze to death. Only the cockroaches and rats are left to inherit the devastated wasteland of a dying planet. This is not wild science fiction or fantasy. Instead, it is a prophetic view of our ultimate destiny. In fact, this comet impact scenario was a very common event out of the Earth's past. Both comets and asteroids are essentially the leftover debris from the birth of our solar system, when the sun and planets formed over 4.5 billion years ago from a ball of dust remaining after the explosion of a star. Asteroids are irregularly shaped objects ranging in size from a few meters to over 1,000 kilometers in diameter, and are generally found in what's known as the asteroid belt between Mars and Jupiter. Over 3,000 of them have been named and cataloged, and astronomers believe that there are 100,000 or more that can be seen.
There's another population whose existence was only discovered about 65 years ago, and that's the Earth-crossing asteroid population. The population of Earth-crossing asteroids constitute a giant swarm of objects, which may be as numerous almost as the main asteroid belt. It's just that we haven't discovered very many of them. It's just an enormous population. You have tens of millions, maybe 100 million, which are larger than a small house. It's just a huge swarm. Every once in a very long while, they can collide with our planet. The asteroid collision hazard is real.
As a result of the overlapping orbits of these Earth-crossing asteroids, tens of thousands of collisions have occurred throughout Earth's history. A future major impact can occur at any time. In contrast, comets are made of ice and rock. Their spectacular tails occur when the solar wind evaporates bits of ice and dust and blows these particles back from millions of miles. Scientists believe there are trillions of comets beyond the furthest planet in a formation known as the Oort cloud, and that comets are periodically dislodged from their distant orbits and hurled toward the sun. Many comets make only one pass through the inner solar system during their lifetimes. Because of the highly irregular orbits of most comets and asteroids, the majority of them go unnoticed until they're practically on top of us. Take, for example, Japanese amateur astronomer Yuji Hayakotake, who in January 1996, using only binoculars, discovered a comet large enough to destroy all life on Earth only a few weeks before its closest approach. Named after its discoverer, Comet Hayakotake was well over 5 kilometers in diameter when it passed to within only 15 million kilometers from Earth, a near miss in astronomical terms. Earth and the other planets in our solar system are essentially huge targets in a cosmic shooting gallery, and have been so since the beginning of the solar system. A look at the moon shows just how many impacts both the Earth and moon endured throughout history. We can appreciate the tremendous extent of cosmic bombardment by looking at the results of such impacts on some of our neighboring planets. In mid-July 1994, telescopes around the world were focused on the planet Jupiter. People worldwide were witness to the most spectacular astronomical event in recorded history. A string of over 20 ice and rock fragments from an ancient comet smashed into the planet Jupiter. Astronomer Carolyn Shoemaker, geologist Gene Shoemaker, and amateur astronomer David Levy discovered the comet in March 1993 during a survey of the sky at the Mount Palomar Observatory. At the time, no one was sure what effect these impacts were going to have on Jupiter.
At one point some months ago, we thought the largest might be about 3, maybe even 4 kilometers across. If they were that large, then altogether these comets would deliver about 100 million megatons of energy.
Shortly after the comet's discovery, astronomers at the Massachusetts Institute of Technology ran numerous computer simulations on the possible impact locations and effects on the planet. The comet fragments were to impact Jupiter over a period of 6 days, although these impacts would occur out of view from the Earth. Fortunately, the Galileo spacecraft en route to Jupiter was in a perfect position to view these impacts head-on. The spacecraft was able to transmit incredible images and data of the impacts. As a result, we learned that each of these explosions affected an area larger than the entire Earth. Had any one of the impacts occurred here, all life forms would have unquestionably been extinguished.
Thank goodness we had grandstand seats for this. Otherwise, these Earth-sized impacts would have completely swallowed up our planet. We would not be here talking about it.
In 1986, the Voyager 2 spacecraft made a very close flyby of the seventh planet Uranus, a huge gas planet with rings and dozens of moons. This probe confirmed earlier reports that the planet was somehow knocked over on its side, with the south pole facing the sun. It has been suggested that Uranus suffered a major impact with a huge object of even greater force than the Shoemaker-Levy comet had on Jupiter. The impact with Uranus knocked the planet on its side, creating the rings and moons from the debris of the impact. The tremendous amount of energy of an impact required to knock a huge planet like Uranus on its side would most certainly have reduced the Earth to rubble had the impact occurred here. Closer to home, rocks brought back from the moon's surface by the Apollo astronauts indicate that the Earth was the subject of a major impact in its distant past.
Very early in the Earth's history, we are fairly sure it was struck by an object about the size of the planet Mars, which ruptured the planet, ejected a great deal of material into orbit around the Earth, and it is that ejected material from a giant impact that ultimately formed the moon.
By just looking at all of the craters on the moon's surface, it's clear that our neighboring satellite has endured thousands upon thousands of impacts. Since the Earth has over 20 times the moon's surface area, there simply must have been tens of thousands of impacts on the Earth as well. Perhaps the most famous and extensively documented major impact event here on Earth occurred about 65 million years ago. Scientists believe that either an asteroid or comet measuring at least 10 kilometers in diameter hit the Yucatan Peninsula, leaving a crater 200 kilometers across, which is now buried under new sediments. This huge crater fractured the limestone rock that underlies the region for a distance of several hundred kilometers. Although there is little question as to the occurrence of this impact event, paleontologists still hotly debate whether or not this impact caused the extinction of the dinosaurs. However, geological evidence indicates clearly that well over 75% of all plant and animal species on Earth were extinguished almost immediately after this impact.
Sometimes people talk about the debate about how long it took for the dinosaurs to become extinct. Was it thousands of years or millions of years? I think probably the dinosaurs went extinct in between 30 and 40 minutes, about the length of time it took for this global heat pulse to roast any creatures that were above the ground and were exposed to this flash of heat.
As if the global thermal heat pulse and long-term winter weren't bad enough to disrupt the ecological balance of the planet, Scientists now believe that this impact had yet another detrimental effect.
Various people have demonstrated that the basement rock at the Yucatan is indeed limestone, but it's a sulfur-rich limestone. And when this sulfur was dredged up and blanketed the globe, it formed sulfuric acid in the Earth's atmosphere, and this caused the sulfuric acid rain, which was quite harmful to the life forms, plant and animal on Earth.
It is most ironic that the carnage and devastation caused by this impact event paved the way for other animal and plant species to evolve into many of the life forms we know today, including our own ancestors. Virtually all of the other traces of impacts endured by the Earth are erased almost as quickly as they appear, such that all impacts, except the most recent, go unnoticed.
Perhaps the best known example is Meteor Crater in Arizona. That was made by an impact of an iron object about 100 feet across. And it exploded with an energy that we can estimate from the crater itself as about 15 megatons, about the size of the largest nuclear bombs. It left a scar. It's 50,000 years old, and there are half dozen other craters on the Earth of similar age that are also easily seen.
One of the most recent impact events on Earth occurred in a very remote and uninhabited part of Tunguska, Siberia in June 1908. A relatively small asteroid the size of a 25-story building, made up of a loose conglomeration of small rocks, became so hot from the friction as it entered the Earth's atmosphere that the asteroid itself came apart and exploded in a massive ball of fire before it even hit the ground. The explosion flattened and set fire to thousands of square miles of forests. It wasn't until the late 1950s that reporters were allowed into the area, and from their pictures, scientists were finally able to piece together what had happened. If the same type of object would hit New York or other highly populated areas, there would most certainly be deaths and casualties in the tens of millions. However, not all asteroids and comets should be viewed as dangerous or harmful to the health of the human species. Scientists now believe that we owe our very existence to these heavenly bodies. Furthermore, they quite possibly could hold extractable resources exceeding our wildest dreams.
I think we have to keep in mind that these objects are interesting from very positive points of view. We can be exploring these most accessible, very interesting, fascinating new worlds now, whereas the chances of having to worry about a collision during our lifetimes is extremely small. It's not something we should ignore, but it should not have precedence over the promise of these objects as targets of exploration during the next millennium.
Perhaps one reason to explore and further understand comets stems from their probable contributions to our own origins. Scientists have calculated that the oceans of the world and most of the other waters on Earth were delivered here by comets.
Planets were being heavily bombarded, and we see the record of that on the lunar surface. Look at the surface of the moon and all those craters. They reflect that shooting gallery that the Earth, that the solar system was 3.8 billion years ago, as comets and asteroids were being scattered around, as the debris from the planetary formation epoch was being swept clear of the solar system. That period was when the flux of comets would have been the most intense, when any cometary contribution to the Earth was at its peak.
Tens of thousands of large comets impacted the Earth in its early history, depositing a huge amount of water that created our oceans. Recent studies of Halley's and other comets conclusively tie certain isotopes of hydrogen found in most comets with those found in the oceans, a sort of chemical fingerprint. Chemical fingerprint. So the next time someone drinks a glass of water, they're essentially drinking part of an ancient comet that impacted with the Earth billions of years ago. Exciting recent discoveries of organic compounds in comets further suggest that they may also be responsible for bringing the spark of life to Earth and provide yet another compelling reason to study these cosmic travelers. For example, water vapor was found on Halley's Comet, which led to the search for organic molecules in other comets. As a result of various studies in the comets Halley, Hyakutake, and Hale-Bopp, a variety of organic molecules have been discovered, such as methyl alcohol and methane, among others.
One of the main constituents of comets is the organic solid material in them. Now, organic molecules are molecules that contain hydrogen and carbon, often in combination with other things, but lots of hydrogen and lots of carbon. And these are the molecules that are especially interesting in the context of the origin of life on our planet and possibly elsewhere in the solar system or elsewhere in the galaxy as well.
One of the mysteries of the Earth, as we've explored its geological record, is how soon life appears. Earth forms 4.5 billion years ago. The tail off of the formation of the Earth is about 3.8. And right away, we see evidence for life. There's definite evidence for life at 3.5 billion years ago, and there's good suggestive evidence in the carbon isotope record for life at 3.8. So it's looking like the Earth is forming and life is appearing very rapidly, instantly, geologically speaking.
So when we see these organic compounds in cometary nuclei, the methyl alcohol, formaldehyde, ethane, methane, we know that some of these were delivered directly to the Earth by the impact of comets. And this tells us that we didn't need lightning storms and complex processing of a methane ammonia atmosphere on the Earth in order to make these complex carbon, oxygen, nitrogen compounds, which are the precursors to biology, to life. They were actually delivered here by the impact of comets.
We can imagine that on comets, there might be the precursors to important biological molecules. For example, there might be hydrogen cyanide and formaldehyde, and these very simple organic molecules. When those molecules were brought to the Earth, they were mixed in the liquid water broth, where they reacted to form sugars and amino acids and other things. So we can imagine that the raw ingredients were in the comets, but the soup, the primordial soup, was made on Earth in the liquid water. So that's one way in which comets could have brought the basic building blocks of life to Earth.
If our oceans were deposited here by comet impacts, then the other planets of our inner solar system should also have received their quota of comet impacts as well. It is not difficult to see how life could evolve on other planets, such as Mars. Early life on Mars could easily have evolved along the same lines as Earth.
Mars, we're confident, once had a lot of water, because we see the geological evidence for flowing water, possibly for glaciers and other things that were created by moving water in a liquid form. But we know that it doesn't have any liquid water now, so we think that it has all evaporated or has seeped into the ground and is frozen as permafrost. Venus, on the other hand, must have received water from comets as well, but we are fairly confident that it's been so hot on Venus for all of its existence that the water had readily boiled away and is simply not stable because Venus is so hot.
There are some scientists who even believe that life forms themselves could be transferred from one planet to another by such impacts.
So people have begun to rethink of the notion that maybe life is more widespread than we realize, and that maybe, imagine a planet somewhere far away. There's life on that planet. And the impact slams into the surface of that planet, knocks a piece of rock up and out. That rock is carrying organisms from that planet. They get carried into space. By one process or another, they're ejected from the solar system of origin and carried through interstellar space, ultimately to come slamming through our own solar system and landing on Earth. That's a direct way to transfer life from one solar system to another.
It has been suggested that fossilized life forms embedded in rocks from Mars were delivered to the Earth in the same exact manner, raising the possibility that living organisms may similarly be transferred. Everything that we've learned about comets and asteroids provides a better understanding of ourselves and our place in the universe. Comets and asteroids may also represent stepping stones to the solar system as potential resources that could be exploited for space travel.
The most valuable thing is the thing we most often take for granted, the air we breathe and the water we drink. This is what comets have in abundance. And I believe that to a spacefaring race, those having a ready source of those things that can support life, that have minerals and metals and the life-supporting materials available in easily extractable form, that is in fact the true value of these things for space exploration in the near future.
For these reasons, several countries are stepping up their studies of comets and asteroids by sending out probes and satellites. Future plans include unmanned sample return missions and even human exploration missions. The first of these studies is NASA's mission NEAR, which launched in early 1996 for a near-Earth asteroid rendezvous. This mission will attempt a close encounter with a 20-kilometer-wide asteroid. NASA hopes to send the probe to within 350 kilometers of this potato-shaped object known as Matilda. Perhaps the most exciting mission to an asteroid has been proposed by Japan. This plan would include sending a spacecraft to actually land on an asteroid and bring back a small sample for analysis.
We have a series of missions to the solar system. We shall have a mission to the asteroid Nereus. The launch is planned for the early 2002.
It will take a number of years for the probe to approach the asteroid, then orbit it briefly to scan its surface, and then finally to land on it.
In the case of the asteroid, we are targeting toward a very, very small object, and we have to be very careful to tap its surface and pick up some samples. And escape is not difficult because its gravity is very small. From the asteroid, we can observe the composition of the very primordial substances in the solar system.
This mission is a necessary first step toward a human exploration mission and potential exploitation of such asteroids for their minerals.
We like to study all the entities in the solar system. So we tend to take this mission as a first step toward our expanding exploration into the solar system. And as a Japanese space activities as a whole, there are studies toward the future manned flight, but at this moment there are no concrete plans as yet.
Another sample return mission, called Stardust, has already been approved by NASA for a rendezvous with a comet known as Wild 2.
We send our Stardust spacecraft flying past the comet. We don't land on the comet. We just fly past it as slowly as we can, about 6 kilometers per second. And we expose this magic material called silica aerogel, which is like a low-density glass material. And the particles surrounding the comet impact themselves into this aerogel during the flyby, and that's what we bring back.
This array will catch the comet's particles much like a fly swatter. Microscopic-sized dust particles penetrate one side of the aerogel, becoming embedded and protected while leaving a fluorescent track.
It's pretty much like a police forensic lab taking a gun and shooting a bullet into a box full of cotton in order to grab the bullet. That's basically what we're doing, except we're doing it at a much higher speed. 6 kilometers per second is a very low speed for a flyby of a spacecraft, but it's much faster than the fastest spinning bullets. And so it is a technological challenge to do this.
After intercepting with a comet, the Stardust probe will transport the material back to Earth in 2006. The probe will detach a pod carrying the cometary material, landing in the Utah desert. Since the materials comprising comets are believed to be the least changed since the very beginnings of the solar system, these particles will be analyzed for clues to planet formation and early evolution of our solar system. The European Space Agency, or ESA, also has plans for sending a space probe to a comet for a long-term mission.
They had flown a couple of years ago a very successful mission called Giotto to Comet Halley, and they now just want to, which was a fast flyby. Now ESA is just going out to launch in 2003 spacecraft towards another comet, but for a rendezvous mission, and see how the comet develops, how it evolves and emits gas and dust and things like that.
After these unmanned probes have completed their missions, the next step would be to send a human exploration mission to actually land on a near-Earth asteroid.
A human mission to Mars would be expensive, it would take a long time, and it would be very difficult. A human mission to an Earth-crossing asteroid would take less time, it would be less expensive, and it would be less difficult in every way. It would be a lot less dangerous. And that's one of the reasons that before we go to Mars, we're going to have to practice on an Earth-crossing asteroid.
Theoretically, with so many diverse resources available on comets and asteroids, it should be easier and cheaper to establish a permanent presence on these bodies than attempting the same on a distant planet like Mars. It may even be possible to establish highly profitable mining colonies on comets and asteroids.
What they're made out of is really very tantalizing. Their compositions can range from solid metallic alloy on one hand, which, by the way, would almost certainly contain trace amounts of gold and platinum, all the way to the other extreme of extinct cometary nuclei, and we think some 10% of the Earth-crossing asteroids must be extinct cometary nuclei, and although they're going to be dark on the outside, they're going to have interiors made up of water ice.
Well, the feedstock for petrochemicals is hydrocarbons, ethane, methane, and so forth. And so what we can now show is that these comet nuclei contain all of the chemicals needed to sustain life and also to support a rather prosperous petrochemical industry in space. And this means that the dream of pioneers on building space colonies that could be self-sustaining is not so far-fetched after all.
And then there are others that are made of different compositions of rock, including some that have organic compounds, very complex organics, which also would contain maybe chemically bound water, but also could be used to grow food, to develop biomass for growing food. So these are the natural resources of space. No doubt about it, they are the gold mines of the solar system.
If the human species is to truly become a spacefaring nation with colonies on Mars or one of Saturn's moons, then comets and asteroids may have...
If
if we could locate one of these in close proximity to a comet nucleus that was far enough from the sun so that it was not actively sublimating material, it was just an inactive ball of ices of these various kinds, then that material could actually be, if you like, mined or extracted in a rather simple way and used for the purposes of the humans occupying that colony. And this could make such a colony self-sufficient and relatively independent from Earth.
On a more practical note, scientists are developing ideas to use comets in establishing long-term colonies on Mars. They may possibly help speed the process by which Mars could become more Earth-like, with water oceans and a more dense atmosphere.
Mars is a very dry place, but it's not too cold. It's not such a terrible place for life to thrive, human life even, if there were enough water and if it were just a bit warmer. What about the possibility of causing a comet or two or three to collide with Mars, give it an atmosphere, give it a hydrosphere, an ocean, and thereby make it a habitable place?
So we've been looking at the possibility that one could move a comet from the outer solar system and gently, slowly move it in to the surface of Mars, break it up, and let the pieces enter into the Mars atmosphere, where they, of course, would warm up and melt. And that would be a short-lived but very important rain on the surface of Mars. And a few of those could bring Mars an ocean again and provide it an atmosphere and make it an Earth-like world.
If we are serious about trying to have our species survive, we may need, in the long term, to look for another place where humans can thrive. And Mars, changed by the generation of a hydrosphere and an atmosphere, may be just the place.
It is vital to the future of the human race that we learn all we can about these cosmic travelers. We must scan the heavens with telescopes and chart their locations. It is imperative that we explore them with unmanned probes, and ultimately to send a human exploration mission to land on one of them before one of them lands on us.